Hey everyone, what we're doing here today is trying to distinguish the difference between altitude, azimuth, and right ascension declination and how it pertains to us in observational astronomy. We went outside and showed you that you can communicate with people where things are by using your hands. You can see the 1 degree, 5 degree, 10 degree, and 15 degree mark if you stretch your arm out at arm's length and put that hand or fist next to the sky to mark off the different degrees. So if you're unaware, we live on a sphere, and the sphere rotates once a day on its axis and gives us our day-night cycle that we're used to. Since we live on a sphere, what people wanted to do was divide up the sphere so that they wanted to pinpoint locations. The way humans have split up the planet is one of two ways. The first is latitude, and the way we did latitude was set 0 degrees to be at the equator of the planet and 90 degrees to be at one of the two poles. And in between there, we look at different increments all the way from 0 to 90 or 0 to 90. That is our measure of latitude. To let you know where you are east and west on the planet, what we needed was another system known as longitude to know how far west or east we went. And we had to pick a 0 location for that, and that ended up being Greenwich, England. So 0 degrees goes right down the planet from the North Pole to the South Pole in terms of 0 degrees longitude. 180, fun fact, is all the way on the opposite side of the planet and runs pretty much through the middle of the Pacific Ocean. And when people give you their latitude and longitude, what they'll give you is how far from the equator they are towards the North or South Pole, and they'll also give you how far east or west they are from Greenwich, England. If we wanted to find Penn Trafford's location, we are 40 degrees north in our latitude, so we'd have to come up 40 degrees from the equator, and we're about 79 degrees west of Greenwich. So here's Greenwich. West is heading towards the Americas, and east is heading towards Asia. If I go 79 degrees west, 40 degrees north, this is my location, and that is where we're standing right at this point. When you walk outside, though, what you create for yourself is what we call the celestial sphere. The celestial sphere is basically your viewpoint centered on you, with a horizon that goes out around you and an altitude from said horizon all the way to straight above your head. So let me kind of point this out and demonstrate. So here we are, North America, and I put a little stick figure to show you that this is where I am on the planet, and I'm going to put myself straight up and down, and when I step outside, I said I create that celestial sphere. This is what you can envision. Here you are standing at the center of your celestial sphere, and there are two coordinates that can happen in this system: the altitude system and the azimuth system. The azimuth system is simply a system that goes 360 degrees around your horizon, with 0 degrees being towards the north, 180 degrees pointing towards the South Pole, 90 degrees pointing towards the east or the Atlantic Ocean, and 270 degrees going west towards the Pacific Ocean. So when you step outside, the north, south, east, west cardinal directions that you know are 90 degrees apart from each other in your azimuth system. If you want to know how high something is in the sky in your celestial sphere, you go from the horizon and use the hand system that we just taught you. To get from the horizon to right above your head, that's a 90-degree angle. That takes about 9 fists to go from this side all the way to straight up over your head. And that location we call zenith. So if I ever tell you to go look outside and look towards zenith, that's where you're looking for. To show you this in what we saw in the planetarium, we have a program I'd like you to open on a browser, and that's known as Stellarium. So when you open Stellarium, there's a couple options that you can have here. You can set your location down here in the left corner and pick the location of where you're at on the planet. You can also select over here on the right the time and date that you'd like to do your observations. And then you have other options down along the bottom here. And it gives you an equatorial grid and an azimuthal grid, which is what we just talked about, with altitude being the height you can see over here above the horizon. So there's 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70, 80, and there's zenith straight up overhead. That is unique to every person on the planet. Why is that unique? If you look back to the globe here, if I lived down in South America and I walked outside, this is my altitude-azimuth celestial sphere. You can see that it has a completely different zenith, and heading towards the North Pole puts us closer to the equator, while heading towards the south puts us towards the South Pole. So the altitude-azimuth grid is unique to each person that walks outside and wherever you are on the planet. So in here, just like we did in the planetarium, what you can do is click on any object that is in the sky, and when you click on that object, you should get some information about it. Like right now, it tells us that the sun has an altitude of 189, which is just a little towards the west from south, and a positive 53 degrees in the sky. So if you look, again, here's 20 degrees, 40 degrees, 60 degrees. So yeah, I'd estimate that around 50 degrees there in the sky right now. So if I go outside right at this moment, I'd put my fist out and I'd count 5 fists above the horizon. I'd find the sun, and I would have to find south. And we've talked a couple ways of finding your cardinal directions when you walk outside. So if I was going to actually plot the sun on this system, on this graph that I've given you here, I would come to 53 degrees of altitude. There's about 53. And I'd come to 189 in terms of my azimuth, which is right around here, so just a little west of south, like we talked about, and plot out the sun at this exact location. The good thing about the altitude-azimuth grid is it's good for right now astronomy. So, however, if I fast forward 2 hours in time, you can see the sun has moved. And for geocentric, Earth-centric people, yes, we think we're stationary and nothing ever moves there. But if you look at this globe, as the day rolls along, you can see that the celestial sphere in your altitude-azimuth grid is shifting. Not the stars out there, but you yourself are rotating and getting yourself a new perspective on the sky. But from our Earth-centric view, it looks like the planets, the sun, the stars move through our altitude-azimuth. So now, 2 hours later, I can see that the sun is sitting around 40 degrees of altitude, and in terms of azimuth, it looks like we're sitting at, there's 190, 200, 210, so about 215 degrees of azimuth. So the sun was here at 53 degrees of altitude, 189, and has shifted to, we said, 40 degrees altitude and 215 degrees of azimuth. So the sun has shifted over to this location in 2 hours. And that's what I'd ask you to show me in the planetarium or on Stellarium to track an object as it has moved through the sky and plot it on this graph. This graph is also onto your night sky journals so that you can use it when you go outside and observe things at night. Well, just like we have latitude, longitude here on Earth, astronomers wanted latitude, longitude for the stars. So what we basically did was project, like you see in this animation, the equator out into space and our celestial north and south pole based on the rotation of our planet. So the celestial North Pole is pointing straight at the North Star, while we have the celestial South Pole pointing down towards the large and small Magellanic Cloud. So let me show you what that grid system looks like in Stellarium. So I'm going to take away the azimuthal grid, and I'm going to put back the equatorial grid. So it's this fainter grid that you see here. With this equatorial grid system, the zero line is no longer on the horizon. The zero line is right here, and this is where the equator is projected out into space. And you can see that I can actually see about 20 to 40 degrees below the celestial equator, and I can see all the way, if I come up towards the north, all the way to the north celestial pole. So the North Star is hanging out right here, about 40 degrees above the horizon. So if I go back over to the sun and click on the sun, not only does it give you its altitude azimuth for the sun, it also gives you right here an RA-DEC. It gives you what we call right ascension and declination. Declination is just like latitude and just like altitude. it's how many degrees from a 0 point. This 0 point just happens to be out in space. Here's my 0 degree line for declination, and you can see the sun is a little bit above the 0 line. If I go below the 0 line, we call those negative degrees of declination, and above, positive degrees of declination. So you can see in the coordinates for the sun, it's saying it's about 4 degrees above the celestial equator. But where is it in terms of its longitude? So my longitude for the sun is in hours now, not degrees, of right ascension. And you can see that my line here says 15 hours. The one above it says 16 hours. So this is 14 hours, 13 hours, 12 hours. Here's the 11-hour line. And so I'm about 11 and a half or maybe 11 and a quarter hours of right ascension. The nice thing is, with the right ascension declination system, is that as I move through time, I'll go through hour by hour now. You can see the sun moving off as it does towards the west. But if I count out again, here's my 15-hour line, 14-hour line, 13-hour line, 12-hour line, 11-hour line. It's still about 11 and a quarter hours of right ascension, and still about 4 degrees of declination. The right ascension declination grid does not change for stars, but planets and the sun do wander through this system as we go through our season. So as we let night roll on and the stars come out, you can see that the altitude-azimuth system is still here, and everything is rolling with this grid system. Much different than the azimuth grid system that I just put back on, because now, just like we saw with the sun, things move in this grid system, but the grid stays put, because this is unique to each person that is observing in the night sky. So I encourage you to use the link that I provided here with the video, stellarium-web.org, to use this as your planetarium software when you are home. It looks very similar to what we've done in the classroom. So you can see with the constellation shapes and the constellation artwork, it looks very similar to what we saw in the planetarium. And Stellarium is a great resource you can use for observing what's in your own night sky, as well as reviewing what we talk about in the planetarium. So the big difference in the two systems is that the altitude-azimuth system is unique to your location and time. Those measurements are constantly changing because you are on the spinning, rotating Earth. But just like we showed you with that dome, it is that celestial sphere that is unique to you. The right ascension declination system is a coordinate system that is fixed into the sky and rotates with Earth. So objects rarely ever change their right ascension declination in your lifetime. So I hope this demonstration clears up the difference between the altitude-azimuth system and helps you understand how to complete your work.